Hello? Yep, that's working. Yay. Is that on? Okay, cool. All right, so if I talk like this, that's loud, right? I think I can hear it picking me up. Yes. And whoop, too far. Yeah, hear it. Hello. Nice to see you in 3D. All right.
planetary system. So Meredith got her bachelor degree from Yale, her PhD from Harvard, and was a meter fellow at Berkeley, right when ALMA started. So what a great way to start a career. And so she was recognized for her work, in particular for the Cochrane Scholar Award. She got the Harvard Book Prize, as well as the Bill Swanger Prize for Excellence in Teaching. Today, she will tell us about the release, so planet formation from millions to billions. And in particular, she will tell us about our latest survey, so the ARKS survey using ALMA, which gives us some unprecedented new views on the release and planet formation. So Meredith, the floor is yours.
Thank you very much, Dimitri, for that nice introduction. And thank you all for having me. It's been lovely to visit Caltech today. How's my microphone in the back? Can you guys hear? Okay, thank you. So I wanted to just start off with some questions that help motivate my research. So obviously, I want to know, how do planets form? Why do I care about how planets form? Well, I'm interested in knowing what types of planets are common around other stars, and why do we care about that? We want to know how normal our solar system is. And it's really all motivated by trying to figure out what different types of environments are we making in planetary, ultimately how common are environments where life might thrive in the universe. So those are some of the kind of framing questions that address the work that I do. And we know that there are lots of planets. We've got 8 of them in our solar system. And thanks to the folks locally, we now know that we have over 6,000 exoplanets around other stars. And we find those planets through a variety of different mechanisms. So I love this visualization from when the 5,000th exoplanet was added to the NASA catalog. This is an animation showing the history of exoplanet detections. And you can see that as time goes on, not only have we found more and more planets around other stars, but we've also used a wider and wider variety of techniques to find those planets. So as you watch, you'll see not only the increasing number of planets popping up, but also you'll see the tallies of the different techniques that we use to find those planets slowly ticking up. And right now you can see this is about 2010. This is when I finished my PhD thesis. We still don't have any orbital brightness modulation, no astrometry, no disk kinematics, but those are going to start coming in as we reach the last 10 years. There's Kepler. Kepler just popped up over there. Hi, Kepler. And so, and you can also see the tally of total planet detections now. Oh, there's our first disk kinematics detection. Yay. So we've actually started to be able to detect planets that are embedded in their natal disks using the oceans of the gas around this star. So there it is. I love that. By the way, if you ever want to get a room full of students asking you questions about exoplanets, just show them that video. It's so great how it really spurs their curiosity and asks them like, wait, what's that clump over there? And what's an orbital brightness modulation? And it's really fun. So thanks to all of the exoplanet surveys, we now know that there's at least 1 planet per star on average. Wow, right? That's amazing. So when we look up in the night sky and we see all of those beautiful stars, we know that on average, there's at least 1 planet per star. So the planets outnumber stars in the night sky. But of course, as you all know, our exoplanet surveys are biased towards particular types of planets. All of the different methods are good at finding certain types of planets and not others. And so debris disks can also help us fill gaps in our knowledge of exoplanet populations. So now know that there are lots of planets, and what we really want to understand is, where do they come from? So here's my other kind of video background introduction. This is our overview of star and planet formation. I love this JWST animation. So you all know, right, that stars and planets form in these gorgeous regions, these molecular clouds, in clusters inside these molecular clouds. So as we start to zoom in on giant molecular clouds, we know that stars form when the densest parts of these clouds collapse under the influence of gravity. So we'll start to zoom in on this cloud core here, and you'll see little knots of star and planet formation happening as gravity causes these clouds to collapse. And now you're starting to see some glow in the middle of that cloud. That's the beginning of a protostar that's forming in the center. So now we have our protostar surrounded by something that's starting to resemble a Keplerian disk. It's still got inflow from an envelope. Maybe it has outflows. We're going to see some jets turn on in a moment. There we go. And now eventually all of that, that's kind of the train wreck stage, all of that settles down into what we would call a pre-main sequence star surrounded by a protoplanetary disk. So this is still more or less primordial material left over from the formation of the star. And then that primordial material dissipates and we're left with something that looks more or less like our solar system, a main sequence star, possibly surrounded by a debris disk, possibly including planets. Here comes the planet from the upper left. Where is it? It's going to come. There it is. Hi, planet. Okay. So, so this last stage now is what I'm going on today, is the phase of planet formation. So in our own solar system, this is one of my favorite images of a debris disk. This is our very own debris disk, the zodiacal light. Has anybody here ever seen, how many of you have seen the zodiacal light? Oh, wow. It's Caltech. So it's more people than usual, right? You guys all spend time at dark sky locations. So if you go to a dark sky location and you look at the western horizon right around sunset, you can sometimes see this ghostly finger of light peeking up from the horizon. It's not the Milky Way. If it's not the Milky Way, it's probably the zodiacal light. So this is dust. We now think it's a combination of dust produced from asteroid collisions and also Jupiter family comets in the inner solar system. And we can see it with our eyes because we're essentially bathed in this dust that the sun illuminates around us. But if we were alien astronomers observing our own solar system from a distance, this actually would not be the brightest dust belt. The brightest dust belt would come from the Kuiper belt, the belt that includes Pluto in the outer part of the solar system. Although if we were in fact the alien astronomers, what we would really see looking back at our planetary system is nothing, because our current technology is not sensitive enough to detect our own Kuiper belt around another star. So all of the debris disks that I will show you today are more massive scaled up versions of our solar system's Kuiper belt. And of course, it follows the plane of our solar system. You can see Jupiter and Venus in the same plane as the zodiacal light. It's just kind of a coincidence that the Pleiades are sitting up there. Okay, so why have I called the talk the missing link? This is based on a plot that Phil Armitage showed when he came to give a colloquium at Wesleyan. He was like, look, here's this problem, right? When we want to understand planet formation, we have to understand form over orders of magnitude and size. So in protoplanetary disks, we're seeing dust grains that are sort of microns to centimeters in size, roughly. And we want to know how those dust grains grow to the scale of planets, 1,000-kilometer planets, over timescales from ages of 1 million years all the way to 1 billion years. So there's this gap in age and this gap in size scale. And I was like, Phil, you're kind of forgetting about debris disks, which actually fill this gap in age quite nicely. So they're telling us about stars typically with ages of about 10 million years up through 1 billion years and beyond. And so when we're thinking about the holy grail of understanding planet formation, what we would really love to have is we would really love to know, okay, how do we start with the initial conditions, even down to the class 0 sources, the really young sources? How do we start with the initial conditions for planetary systems and predict the range of planet forming outcomes in such a way that we're consistent with all of the constraints that we get from each of these stages along the way, the protoplanetary disks, the debris disks that are telling us about that evolution from 10 million years through 1 billion years, all the way to the exoplanet systems. There are some younger exoplanet systems that we know about, but by far the majority are out at this billion-year age range. So debris disks have an integral role to play in this process, and they're really telling us about what's happening in this key age range from about 10 million years up to 1 billion years or so. The main tool that I use to do the work that I'll talk about today is ALMA, the Atacama Large Millimeter Submillimeter Array. This is just a gorgeous video of its operation. It's sitting high up in the Atacama Desert, above most of the atmosphere and most of the water vapor that blocks radio light from space. And even though it looks here, I mean, you can kind of see mountains in the distance, it looks like it's down at low altitude. It's in this amazing location called the Altiplano, the high desert plains of northern Chile. So you can spread out your antennas to separations of 15 kilometers and really get these incredibly sharp, detailed views of the radio emission from all kinds of different things, including planet forming systems. So just again, for scale, each of these antennas there's a little person up there. Each of these antennas is 12 meters in diameter, roughly the size of a small house. And they pick them up and drive them all around the Altiplano in northern Chile to go from the longest baselines to the shortest baselines and back. So the project that I want to talk to you guys about today is this large program that I've been working on with ALMA for the last 2-3 years now. It's called ARKS, the ALMA survey to resolve exoKuiper belt substructure. So I'm just going to start by breaking down what this long jargon-filled title means. So first, I've already told you a little bit about exoKuiper belts. That's another name for debris disks. These are scaled up versions of our own solar system's Kuiper belt. They're more massive versions, like I said before. And why is this hard? It's hard because you've probably seen images of rings and gaps in protoplanetary disks. But on average, debris disks are 1 to 3 orders of magnitude fainter than protoplanetary disks. So it's a lot harder to get that high resolution data just because the surface brightness is so low. Also, debris disks are typically after the first wave of planets have formed. We now know for sure, because we can see them, that there are planets embedded in protoplanetary disks. But these are ages in our solar system around the time when the moon forming impact occurred and around the time when most of the cratering record on the kind of dry airless worlds was set. So, we don't think there was probably a late heavy bombardment anymore, but the cratering record dates back to these first few 100 million years where a lot of things were smacking into each other as the kind of debris that was left over from the formation of planets was cleared from the solar system. So that's exoKuiper belts. Why do we care about substructures? So I'm guessing many of you have seen this image before. This image is iconic. It's now in most intro astronomy textbooks. It started as a test of ALMA's longest baseline configuration. So back when ALMA was first expanding to go to its longest 15-kilometer baselines, they needed some objects that they could observe at high angular resolution. And they thought, okay, here's this HL Tau protoplanetary disk. It's kind of bright and looks kind of smooth and fluffy, so that would be a good target. And they imaged it and immediately saw these rings and gaps, which we had sort of imagined were in planet-forming disks, but we had never seen before ALMA came online. So this told us that there were rings and gaps in protoplanetary disks. We now know about a lot of them. I'll show you some more later on. But basically, before the ARKS survey with ALMA, here's what we knew about the distribution of widths. This histogram is going to come back to haunt you, so it's worth paying a little bit of attention right now to what's going on in this plot. So on the x-axis here, we have the fractional width, which is how broad is a ring compared to its distance from the star. So the orange is the protoplanetary disk ring. So this is basically the D-sharp sample. Again, I'll show you that in a minute. And before ARKS, what we knew about debris disks is encapsulated by this blue histogram. So the distributions looked very different. But the big caveat here is that the blue histogram was made with blurry vision. We only had low resolution observations of large numbers of debris disks pre-ARKS. And so we couldn't tell whether these are actually wider or whether there were unresolved substructures that we were missing because we were observing at too low an angular resolution. So this is one of the big motivating questions behind ARKS. So this is kind of enumerating some of the other big motivating questions behind ARKS. We want to know, how does the radial structure of planetary systems evolve on these timescales, tens of years to billions of years? Is it really different from the protoplanetary disks, or to what extent do debris disks actually inherit their structure from the protoplanetary disk phase? We wanted to learn about vertical structure. I'll talk more about this in a minute. How common are Uranus and Neptune analogs? The vertical structure can actually tell us something about the prevalence of Uranus and Neptune analogs. I'll explain that more in a minute. We want that we see late stage, where does it come from? What is it made of? And it's hiding that we could detect through that disk kinematic method that was on the planet slide before. And so to do all of these things, our big needs were, we needed high angular resolution so that we could resolve the smaller fractional widths. And we also needed a decent sample size to be able to say something statistical about the structures that we're seeing in debris disks. So all of that points to the need for an ALMA large program. So this is the ALMA survey. Here's a part of the team assembled in Dublin in the summer of 2023. So the PI of the program is Seba Marino. Luca Matra and I are co-PIs on the program. So there's Seba, Luca, and me. And then we also have team leads, Julien Milly, who led the scattered light analysis, Mark Wyatt, and Torsten Luna, who led the theory part of the analysis. So overall, the team comprises 55 members from 34 different institutions, 290 hours of ALMA time. It included 18 new high-resolution debris disk targets, plus 6 that we deemed sufficiently well-resolved in the archive. And our goal was basically to be able to resolve down to the level of the Kuiper belt, or the fractional width of the Kuiper belt, or the typical width of a protoplanetary disk ring. And then we also got some high-resolution gas observations in 5 of the systems. So I'm going to talk about 3 different science themes coming out of this project. So just to give you an idea of where the project is, we submitted our first round of 10 paper drafts in the summer. About half of them have been accepted so far. And so I'm going to try to summarize some of the major results, but I'm going to organize them along these 3 science themes. So first, we'll talk about disk structures beyond the protoplanetary disk phase. So as promised, protoplanetary disks we know are full of structure. This is the D-Sharp survey led by Sean Andrews. And this was, so after the HL tau image, basically this was our response to go back and say to ALMA, hey, we now know that there are gaps in rings, but we need to be able to see, are those common or not? And so we basically selected for flux. So these are some of the brightest protoplanetary disks, and wanted to see, hey, are there rings and gaps in more of these systems? And yes, structure is everywhere in these big, bright protoplanetary disks. And this led to a lot of excitement because people wanted to look at this image and say, oh, I see a planet here. And oh, there's a planet here. And oh, there are 2 planets here. And oh, planets everywhere, right? But there's really a chicken and an egg problem that happens with these protoplanetary disks, which is that we think that substructures are really important in the planet formation process. They may even be necessary to form the planets, but we think that planets might be necessary to form the substructures. So we actually don't know which comes first, the planets or the substructures. And there's been a lot of work over the last 10 years trying to look at what is actually causing these substructures. We know that it's intimately entwined with the formation of planets in these systems, but you can't just look at a gap and say there's a planet in that gap, right? It's probably more complicated than that. But still, we know that these are related to the formation of planetary systems, and so we want to study how these structures evolve at later stages. So with debris disks, this was the state of the art pre-ALMA, and you can see this is actually pretty good, right? This was the Reason survey, led by Luca Matra, which brought together basically all of the blurry images of debris disks that had been observed with ALMA and the sub-millimeter array. And it was actually just published in February of this year. And there are a lot of other papers and reviews on this subject that you could check out. But basically what we knew pre-ARKS was that small belts seem to deplete faster. So we had some evidence for collisional evolution in these systems. Some debris disks we know have halos of small grains. There's some amount of blowout of the small grains. And disk luminosity drops precipitously after 10 million years. So you see a real transition around the 10 million year age range. There are certainly stragglers on either end, right? There's some young debris disks, there's some old protoplanetary, but on a population level, there seems to be a transition around 10 million years. And some of them have substructures, right? We knew about a couple with rings, like HD 92945 was one of them. 107146 is a really iconic one. But again, our observations at this point were too blurry to reveal much in the way of substructure. So without further ado, I'll show you the updated ARKS system. So this is 24 debris disks. And so these are the largest collection of high resolution images of debris disks to date at millimeter wavelengths. So here they are. So I put Yunno's picture down here. Yunno's a postdoc here. There he is up in the back. Hi, Yunno. So Yunno led the radial structure paper for ARKS. And so this is the gallery that goes, I think it's in both Seba's paper and Yunno's paper probably. But this is our gallery of images. And so some of the headline results here is that even just looking at this with your eyes, you can probably tell that while there are certainly some disks with really narrow rings, right? Those small fractional widths like we see in the protoplanetary disks, there are also disks that really are just big and fluffy, where we're actually not seeing a whole lot of structure. They're big and they're broad. And the 95086 is another one over here. So some dust belts are actually just wide and fluffy, unlike protoplanetary disks. But at high resolution, more of those rings are narrow. So now if I go and update that histogram that I showed you before, where we had asked this question, are these actually wide belts or are they unresolved substructures? Now you can see the answer in Yunno's paper. The answer is a little of both, right? Where now the updated histogram in the ARKS era shows that actually the histogram is more closely aligned of exoKuiper belts, is more closely aligned with the protoplanetary disk rings, but there's this population of kind of big fluffy disks, big wide things. And I'll talk a little bit more about the implications of that in a minute. One of the things that my group did a lot of was parametric modeling. So these are some of the results. This was my master's student, Elias, and who's now a PhD student at UC Berkeley, and Jamar is now a PhD student at Stanford. And this was work that they did in their theses. So on the left are the data images. In the center column is the best fit model image. And on the right is the residuals, which if they've done their modeling properly should look like noise, and they basically do look like noise. So they did a lot of parametric modeling, and from the parametric modeling that my group did and the non-parametric modeling that led, we were able to learn a little bit more about the details of the dust structures that we were seeing. So the first result here is that we were able to kind of identify some families of substructures. So good news for astronomers, a lot of things are well reproduced by power laws. We all love power laws, right? So a lot of things are radially power laws. We did, though, see a lot of things that were better fit by a combination of Gaussians, double Gaussians, and that took two forms. So sometimes we see two concentric rings that are well described by Gaussians. And then sometimes we would see something that we hadn't really seen before and hadn't really expected to see in our sample, which was a narrow ring with sort of a much broader halo that was slightly offset to larger radii. So, so we saw a lot of this kind of narrow ring, big broad halo that was often best fit by a double Gaussian in our parametric. And then we had a few that had other. It's a combination of power laws and double Gaussian structures. The other plot that I thought was really cool that came out of this modeling is, this is maybe my favorite plot that came out of ARKS. I don't know, there's another one coming up soon that I really like also. But on the y-axis here is the slope of the inner edge of the debris ring. So a large number means a steep slope and a small number means a shallow slope. And then on the x-axis is the inner radius. And you can see that this actually pretty neatly divides into two groups of disks where we have relatively small disks with sharp inner edges, and then we have really large disks with shallow inner edges. And so the interesting thing about this is I was naive thinking about this plot at first, and maybe you are in the same way, which is I thought, well, sharp edges surely are carved by large planets. So maybe that's what we're seeing, is that all the large planets are interior. And then I learned from my dynamicist colleagues that I was completely wrong and backwards, and that actually the large planets should carve shallower edge slopes. And the reason for that is because large planets are really good at exciting planetesimals and resonances into eccentric orbits, and that actually kind of smears out the inner edge of the debris ring. And so, so what we're seeing here is probably a population, it's suggestive of a population of planet-sculpted objects. And indeed, if you look at the three systems that we know have directly imaged planets in our sample, Beta Pic, HR 8799, and HD 95086, they're all part of this large, shallow inner edge cluster of systems. So I'm now very excited about looking for planets in these other systems, which have largely been ignored by the direct imaging community for reasons that I don't fully understand, except that they're a little older. So you can see here, they're kind of color-coded. Oh, wait, actually this one. The version in the paper is color-coded by age. Some of these are a little bit older. So more like on the tens to hundreds of millions of year timescales. But you can still, I mean, like JWST is very sensitive to low masses edges. So I think that's an exciting population to search for more planets. We also know that some are asymmetric. This is something that was also really hard to see in the low resolution blurry images. And in fact, we now know that mostly the asymmetric sources are the gas bearing sources. So we're seeing the impact of late stage gas on the motion of dust grains in these systems. We see examples like this, where there's an arc on one side. This looks an awful lot like a hydrodynamic vortex, like you've seen in some protoplanetary disks. We see others that are eccentric. That's something that you expect to see from planets, but could also be caused by gas. And then this is my favorite asymmetry. We've never seen anything like this in a debris disk before. You kind of have to squint at this one, but I'll show you why I don't think the squinting is important, right? So this is 49 Ceti, also known as HD 9672, one of the prototypical gas-bearing debris disks. And you can see that if we carefully draw the major axis in white here, there's a twist to where the continuum peaks kind of above and below the major axis. And maybe you're like, I don't think that's real. But if you look back to a paper that I wrote in 2017, where we looked at, we subtracted off the best fit Keplerian model and looked at the residuals for the gas in the disk, it does exactly the same twist, where the gas residuals are following the dust residuals kind of above and below that major axis of the disk. So we're actually seeing some kind of warp or spiral structure in both gas and dust in a debris disk, which we've never seen before. So now I have a master's student working with me on trying to model this and interpret it and tell us what it's telling us about the dynamics of the system. Yes. This is one, right? That's it. In the debris disk, so among debris disks, we now have a set of roughly 24 debris disks that we know have gas. Only 5 in the ARKS sample have been imaged at this high in angular resolution, and of those, only 1 shows this type of asymmetry. So it's a small subset of a relatively small sample. Yeah, exactly. It's the beginning. That's a nice way to say it. Yes. And then, okay, so moving on to scattered light, which I know a lot of you here are interested in. We're seeing evidence for grain size segregation in the scattered light, again, primarily in the gas-bearing targets. So, whoops. So this is, oh yeah, just to explain what this is. The colors here are the scattered light images. This is a paper led by Julien Milly, and the contours are the ALMA. So you can see that in some cases it traces really nicely. That's HR 4796. But we can see when you look at the profiles really carefully, you can see that the gas-bearing systems almost all show the micron-sized grains peaking farther from the star than the millimeter-sized grains. So there's actually, a lot of times in protoplanetary disks, we'll talk about gas drag acting on the dust. Here, it's almost the opposite, that the gas pressure gradients are pushing the dust out to larger radii, the smaller dust grains out to larger radii. There's one exception. Only HD 61005 shows micron-sized grains peaking interior to the millimeter-sized grains. For the gas-poor targets, they're all located at exactly the same radius. So the other systems have these co-located micron-sized and millimeter-sized grains. And again, you're getting first results from the survey. So for a lot of these results, they're new and exciting, and we don't have really good interpretations for them yet. But I think the important point here is that the comparison between the scattered light and the millimeter is showing us that the gas has a real impact on the spatial distribution of dust grains in a way that's kind of opposite of what we see in protoplanetary disks. So something that I'm really excited about in the future is looking at direct planet-disk interactions. We have a few examples in the literature. These are some from my students of systems. This is HD 106906, where you can see both a debris disk and a planet, and you can study the dynamical influence of the planet on the disk. This is another one, HD 206893, has a little brown dwarf or massive planet thing embedded in the middle of the disk. And we have really great predictions for high contrast imaging, like with JWST and other systems that will help reveal. I think we're now getting into this really interesting region of parameter space where we've predicted that there should be planets sculpting a lot of these rings. We have predictions for exactly what the sensitivity is. And if we don't see planets, it's starting to rule out really interesting regions of parameter space with JWST. So I don't know, keep your fingers crossed for our JWST proposal this cycle. We really want to try to see if we can actually finally detect that are inside sculpting these disks. Okay, so that's substructure beyond the protoplanetary disk phase. Now I want to talk a little bit about the vertical dimension. That was all radial structure. So the vertical structure is also really interesting. So why should you be interested in resolving vertical structure? At millimeter wavelengths, so people have resolved vertical structure at shorter wavelengths than scattered light, but that's a small grain population that's impacted by a lot of other forces that don't operate at millimeter wavelengths. Things like radiation pressure from the central star. They do operate, they're just not as strong as gravity. So we've got radiation pressure, we've got stellar winds, we've got interactions with the ISM. And so the interpretation of radial structure at shorter wavelengths is quite complicated. In the millimeter, it's simpler because these grains are primarily responding to gravity and they're less sensitive to these other forces. So vertical structure, specifically in the millimeter, tells us a lot about planetary masses and migration histories. And I'm going to give you kind of a cartoonish version about how this works. It is more complicated than this, but this gives you the general idea of what's going on. So on a basic level, if you have a Neptune hidden in your disk or just interior or exterior to your disk, it's every time a dust grain comes near it, it's going to give it a little dynamical kick. And that kick will increase its eccentricity. And then there's some equipartition with inclination that happens, and it'll tend to puff up your disk. So the more mass you have in a disk, the puffier it is. So if your disk is stirred by a Neptune, you get a puffy disk. And if it's just stirred by a few Plutos instead, you get a pretty flat disk. Okay, that's the basic idea. So the vertical height of a disk can be, in the millimeter, can be related to the total gravitational mass embedded within the disk. Also, this is a simulation by Sean Raymond that shows some of the dynamics that might have happened like in an early solar system. But you probably saw that this outermost planet was migrating outward through the planetesimal belt. And you see this very specific signature of that outward migration that we also see in our Kuiper belt, where you have kind of a cold classical belt of planetesimals that have been relatively undisturbed since the formation of the planetary system. And then you get a scattered belt with pumped up eccentricity. And so in our solar system, if you took a vertical cut through the Kuiper belt, you would see at least two different dynamical populations. You see the relatively narrow cold classical belt, and then you also see more vertically extended scattered components of the Kuiper belt. So we might be able to see that in debris disks as well. It's really hard to do these kinds of measurements. So pre-ARKS, there were only two systems that had good enough measurements that we were pretty confident we had resolved the vertical structure. One of those is Beta Pictoris. And in Beta Pictoris, this is work led by Luca Matra. You can actually see it with your eyes here, right? Basically, the dark blue belt is the relatively narrow cold population, and then the light blue stuff above and below showing you that more fluffy scattered population. So we did have one previous example of this same kind of dual structure that we see in the Kuiper belt, and then we also had this work by students in my research group, both now PhD students at University of Illinois, looking at the AU mix system at two different ALMA wavelengths, and looking at how kind of puffy the disk was. Here we found that it was well reproduced by a single Gaussian, but basically it put such a low limit on the total mass in the disk that we couldn't be hiding Uranus and Neptune analogs. So that's telling us that AUMIC does not have Uranus and Neptune analogs, at least not in the kind of 20 to 40 AU region where they exist in our solar system and where the disk would be probing in this system. So we wanted to do this for as much of the ARK sample as we reasonably could. This part was led by the postdoc in my group, Brianna Zawodzki. And so she selected all of the relatively high inclination systems where we could plausibly resolve the vertical structure of these disks, and did a whole lot of modeling, again, in collaboration with Yano, who led the non-parametric modeling. Brianna led the parametric modeling. And whoops, here's basically what she found. So these are all of the vertical profiles that Brianna derived for the disks in our sample that were high enough inclination to do this. So most of the disks were, in fact, spatially resolved in the vertical dimension, which is fun. The inferred masses were mostly pretty low, although there was quite a long tail. So this is a violin plot, which if you don't like violin plots, just pretend it's a histogram. It's basically the same thing, showing that about half the sample, this is the mass of Neptune here, right, or Uranus. And so about half the sample is below that mass, less than a Neptune mass. And about half the sample is above that mass, and including some that were quite vertically extended that seemed to require a lot of mass to be pumping them up. I think the headline result here, though, is that the majority of the sample actually preferred that two-scale structure like we see in the Kuiper belt, where there was kind of a narrow component and a broad component superimposed on one another. And that's something that we hadn't seen before. So just to get into the weeds slightly, the majority prefer a Lorentzian. And the reason that we use a Lorentzian is it has exactly the same number of parameters as a Gaussian, so it makes the statistical comparison a little bit easier. But we also did fit double Gaussian, and you can see that the Lorentzian kind of naturally, that's the orange line here, the Lorentzian sort of naturally reproduces this narrow core and extended wings. So that structure was preferred by a majority of targets in our sample. So that could be telling us that Neptune-like migration is common in other planetary systems. On the horizon, we can do more of this sort of multi-wavelength imaging that I was mentioning. Imaging vertical structure at two widely separated ALMA wavelengths actually tells us about the tensile strengths of bodies in the collision cascade. So whether you have like fluffy aggregates or hard compact spheres for your dust grains, that's a whole other line of investigation. We have some follow-up observations ongoing now with ALMA to do that for the ARKS chart. And then I think, that interpretation of Neptune's outward migration through the Kuiper belt is very tempting, not unique. And so I think there are some really interesting theoretical interpretations on the horizon. This is work done by Antronik Safilian, where he's showing that if you have a disk where the disk mass is about 1/10 of a planet mass, you can actually kind of reproduce naturally that narrow core and wing structure also. That's the orange line that you're seeing here, as opposed to if you have a very massive disk, you just get a single really narrow component here. So there is a little bit of nuance involved in the interpretation of the vertical structure. And what Antronik is doing that's unique to his work is including the self-gravity, the mass of the debris disk in his calculation. So I think as we get better models of the dynamics of these debris disks, we will find alternative interpretations. But we do see this dual spatial scale structure in most of our systems. Okay, and now finally, the last science theme I want to talk about is brief history of gas and debris disks. So my fun fact to start off this section is that we knew about gas and debris disks before we knew about debris disks. So this table comes from Arnie Sledebeck's 1975 paper in AppJ. This is back when AppJ papers were like 2 pages long, and you could write a paper. This paper was titled something like, I'm paraphrasing, but weird stars that I saw in the southern sky. And so it has a table where the column name is just peculiarity, like what was weird about this star. And so the row that I will draw your attention to is Beta Pictoris. And he was like, hey, there were these weird calcium H and K lines that I didn't really expect. That's weird. But then he goes on to say in the paper, like, oh, I guess these are probably interstellar or maybe even circumstellar. And the answer is yes, they were circumstellar gas lines. We didn't even know for sure that there were debris disks yet. And he had already found gas in a debris disk without knowing what it was at the time. So we now know, this is one of Aki Roche's papers where she's showing that the signature of gas in the Beta Pictoris debris disk looks like a lot of what we would see from comets or asteroids in our solar system. So, so we're seeing probably second generation material, although I'll talk more about that later on. ALMA has showed us that gas is actually a common phenomenon in debris disks. This is work that was led by one of my students, Jesse Lehman-Sifry. He's now director of machine learning at the same company that my dentist uses to scan my x-rays for cavities. Isn't that cool? Like, I don't know, one of these cool astronomy connections. I went to my dentist and I was like, wait, that company, that's where my student does machine learning. Wow. So anyway, back when Jesse was an undergraduate, he worked with me on this great paper where he showed that gas is extremely common around young A and B type stars when you observe with ALMA. So we weren't expecting this. People used to say, oh, debris disks, those are the ones without gas, and protoplanetary disks are the ones with gas. And we now know that that's not true, that up to half of young A and B stars do still have substantial reservoirs of molecular gas in their disks. And so we have a lot of questions about that gas. It's probably pretty important. So this is my, like, why should you care about gas and debris disk slide for people who study exoplanet atmosphere. So this is all thanks to theoretical work by Kantan Kral. He has shown that accretion from late-stage gas disks onto planets can alter or even overwrite the composition of exoplanet atmospheres. This is one of the figures from his paper showing for terrestrial planets how little gas accretion it takes to reach the gas to core ratio of present Earth. So you can do it in about 1 million years if you're at 10 to the minus 6 Earth masses per mega year of gas accretion from the debris disk onto the planet. And then similarly, if you care about C to O ratios in exoplanet atmospheres, it can alter the C to O ratio even for giant planets. Again, this is the mass accretion rate on the y-axis and the total atmospheric mass on the x-axis. And this is showing how late-stage gas accretion can alter the C to O ratio in these disks. His most recent paper in 2025 was showing that he thinks he can explain the high metallicities of Uranus and Neptune in our solar system from late-stage gas accretion. So, so if you want to understand the composition of exoplanet atmospheres, you can't ignore the possibility of late-stage accretion from the gas and debris disks. And our problem at this point is we actually have no idea, A, where the gas comes from, or B, what it's made of, because all we can detect is CO. And so there are 2 basic types of interpretation of the gas in these late-stage debris disks. Either it's protoplanetary disk gas that's left over, the disk is refusing to grow up and disperse its gas, so some people call these Peter Pan disks, or it's actually previously incorporated into icy planetesimals and then later released into the gas phase. In this case, there would be basically no molecular hydrogen. It would be carbon and oxygen dominated gas. So we don't know, because it's really hard to figure out the composition, since the only molecule that we can see at this point is carbon monoxide. But this was work by my former master's student, Jessica Kloosmeyer, who we stared at 49 Ceti with ALMA for 5 hours in a bunch of different molecules that are really common in protoplanetary disks or comets, and saw none of them. And also, this is a really nice summary paper by Grigory Smirnov-Pinchikov, comparing the limits that we have on various molecules to models of different gas compositions. And basically what he showed is that we just don't have the sensitivity at this point to reliably distinguish based on the molecular limits alone. And so this is a real challenge, and we have to get kind of clever in trying to figure out what's going on in these systems. I will talk about a few of the ways that evidence is accumulating for a second generation origin. But first, I'll show you the ARKS first results from the gas. So we have this gorgeous high resolution, these are the highest resolution images of gas and debris disks that have ever been taken. I already showed you the wacky asymmetry in 49 SETI, which is unique, and we're still trying to understand what it means. But basically what we found is that in the ARKS sample, the gas extent is generally wider than the dust, especially inwards towards the star. And so we don't know if that's, again, the imprint of the original protoplanetary disk, which has a large radial range, or whether material is getting generated in the planetesimal belt, and then there's a source of viscosity that allows it to accrete inwards onto the central star. But the isotope ratios, I was talking to Catherine about this earlier. I think the isotope ratios are really exciting. We now have 13CO and C18O for a couple of the targets in our sample. And so we can start to look at the isotope ratios and compare them to icy bodies in our solar system. And that's one of the signatures that's suggesting that it's rather than inherited from protoplanetary disks. So there are two papers about gas in ARKS, one led by Sorkin McManaman and the other by Aoife Brennan. And so this is a little aside, but here's another project that I'm working on with my students. I think the gas in debris disks provides a real opportunity to study stellar astrophysics. So we are not the first to do this, but we are the first to do it for debris disk host stars, which are an older and more massive stellar population than people who have previously done dynamical mass modeling. So the idea here is to take Kepler's third law, which is just, the mass of the central star determines how velocity varies as a function of distance from the star. So if you have a gas disk orbiting around your star and you measure velocity as a function of distance, that tells you the stellar mass. It's a really simple idea. So we can do this because ALMA gives you the high angular resolution that you need, and Gaia gives you the extremely precise distances that you need. So you really need both ALMA and Gaia to make this work. There are now 15 of these debris disk host stars with sufficiently well-resolved CO that we can make this measurement. And here are just a few of the examples. We actually, I don't want to mislead you here. We don't just fit the spectra. We fit the full three-dimensional position velocity cube to get the dynamical mass, but the spectra are a nice convenient way of showing it. And what we are finding when we compare the dynamical masses that we measure, and then we put them on stellar evolutionary tracks in an HR diagram, is that some of the systems match reasonably well. This is actually one that matches reasonably well, but we are finding systematically lower dynamical masses than photospheric masses. And I figured I'd mention it here because there might be people here who could help me understand why this is the case. And I think this kind of result has been found for some of the lower mass younger stars, so like the K and M stars around in protoplanetary disk systems, and it seems to have to do with the level of sophistication of modeling magnetic fields in the stellar models. And I think that may be happening, but since this is an older and higher stellar mass population, I'm not sure it's exactly the same thing yet. So this is a cool opportunity to learn about stellar astrophysics that these gas disks present. Okay, so I will actually summarize here and open it up for questions. So basically, we now know that not all debris disks inherit their substructure. There is some amount of radial evolution, and in particular, there are these big fluffy disks that preferentially host directly imaged exoplanets that we think are excellent targets now for direct imaging with high contrast imaging tools like JWST. Vertical substructure is common. That's a big result that comes out of the ARKS survey. We now know that a majority of our systems that we've modeled prefer that vertically narrow and vertically broad distribution of material that's similar to what we see in the Kuiper belt in our own solar system. So maybe also indicating that Neptune-like migration is common. And then we now have the highest resolution images yet of gas in these debris disks. And the isotope ratios are suggesting to us that the gas is likely produced from exocomets rather than inherited from the protoplanetary disks. We see lots of carbon. And that's actually, side note, that's probably why in Jessica's thesis, we didn't see any of these other molecules, is because neutral carbon from further photodissociation. So when you photodissociate CO on the surface of the debris disk, its photodissociation product, neutral carbon, can actually protect the remaining CO from further photodissociation. So that is consistent with what we're seeing in these images as well. So I'll just end by thanking all of the students and postdocs who worked with me on this project, and the funding agencies, may they continue to fund our research. And I'm happy to take any questions that you have.
Is it obvious why there are no
stars?
Yeah, that's a good question. I mean, we do know that debris disk host stars in general are biased towards A stars, which are more likely to be single. But I think that's a question that has potentially many layers to the answer, right? So there is this bias towards A stars. So maybe that's all it is. Maybe it's just that they're A stars, so they're less likely to be binaries. But we also know from protoplanetary disk studies and from some of the exoplanet studies that binarity can impact the rate and location of planet formation. So it could be related to that as well, that you know, you need kind of a special set of binary separations to allow you to form these exoKuiper belts. Yes. Yes, and as I'm racking my brains right now, I don't know, maybe Carl or Tiffany or some of the other debris disk people, can you think of a single binary debris disk, like binary host star for infrared excesses? Yeah, right. Yeah, but how many of those are resolved like with structure? Yeah, I can't think of any of them. Yeah, with ALMA. So that's yeah, it's an interesting point to think about resolving those binary systems. Yeah.
You mentioned
Mm-hmm.
isotope ratios. Isotope ratios have also been proposed as a
Yeah.
mechanism for understanding how giants form. So those isotopes, did you have thoughts on using isotope?
Yeah, that's a really interesting point also that yeah, now that we are starting to see, I mean, I would say the isotope ratio evidence is in the very early stages, right? And there also, at least from my reading of the planetary science literature, there seems to be a pretty wide range of isotope abundances observed in the icy bodies of the solar system alone. So I think that is going to be complicated, but it is promising as an avenue for understanding the impact of this late stage gas accretion. If we did see some of these kind of very far deviated from interstellar medium ratio isotope ratios in some of the exoplanet atmospheres, that's one avenue that might point to the importance of this second stage, this late stage gas accretion as well. Yeah. Yeah, it's an interesting question. So yeah, there's a plot with age on the x-axis and CO luminosity in my 2018 annual reviews article. So it just to interpret that plot for you, basically the ones that are the brightest tend to be at the younger ages, so in the sort of tens of millions of year age range, but we do see gas out up to about 1 billion years or so. So even some of the old debris disks have some gas reservoirs, although they tend to be very, very faint. Yeah, that's fairly consistent with what we see, right? We see it's more common and they're brighter in the young A and B type stars, but there is a tail that goes out quite late in the evolution of these systems. Yeah. Yeah. Yes. Yeah. So the precision of these measurements, oh gosh. I think about it in log mass space, because log stellar mass space, because that's where we sample our priors are log uniform in stellar mass. And so our uncertainties on the stellar mass are typically around 0.01 to 0.001 in log stellar mass. So I would have to think about, I can't do that math on my feet, but that's roughly where our uncertainty range is. So the main limitation tends to be the Gaia parallax uncertainty. So that's something that we fold into our MCMC chain to propagate through to the uncertainties in stellar mass that we derive. And so when we make the plots like this one, this is a 1 sigma dynamical mass range that you're seeing here. The tracks on the upper and lower. This plot is difficult to interpret if you haven't thought about it for a while. So basically, what we're plotting here are stellar evolutionary tracks for the upper and lower mass range. So this one you can see has kind of a 0.03-ish log stellar, no, actually, this is not log. This would be linear, 0.03 solar mass error range. That's 1 sigma. And then these are this is just an HR diagram. So these are the photospheric measurements and the uncertainties that we have in luminosity and temperature. So, so this one is reasonably consistent, right? You can tell that these error bars kind of overlap at the couple sigma level. But we have some that are much more inconsistent, where you see the photospheric properties are really offset. One of the big uncertainties here that I didn't mention was metallicity. I really wish that people would measure precise metallicities of all of these debris disk host stars, because we don't have them for most of the debris disk host stars. So, and that's a significant source of uncertainty in plotting the stellar evolutionary tracks. But the offset is so consistent in terms of its direction, right? That the dynamical masses are coming out lower than what you would infer from the photospheric properties, that it seems like there's something going on there. There's some mismatch between what the stellar models are predicting and what we're actually observing with the dynamical masses. Great. Yeah. So, so the conclusion about the isotope ratio. So that's coming from, we have for a couple of the disks in our sample. This is both the ARKS data and archival data that we have. We now have well-resolved observations of the gas in the disk in several different spectral lines. So we have the J equals 3 to 2 and J equals 2 to 1 transition of CO, 13CO, and C18O. And so some of this is complicated by optical depth, right? Remember that we're looking at debris disks rather than protoplanetary disks, so the overall gas masses are lower, and therefore the optical depths are a lot lower. Probably 12CO is still optically thick in a lot of these systems, but 13CO probably isn't, and C18O definitely isn't. I mean, that's been shown fairly conclusively in some of the papers that have really dug into this. And so we can look at, for example, a 13CO to C18O isotope ratio, and those are probably optically thin line ratios that are actually reflecting the relative abundances of those molecules. We can also model using radio transfer tools to try to account for the different optical depths. And so we're doing that as well. Yeah. So when we look at the 13C to C18 ratios, or 13CO to C18O ratios, we're trying to derive. I mean, so this is folded into our model. We have in there we have the interstellar abundances of 13C to 12C and 16O to 18O, and we kind of monkey around with those in our models, and so we derive ratios that are significantly different from the ISM ratios, but they are similar to what you see for some of the icy bodies in the solar system. Now, I mean, there are a lot of caveats there, because for some protoplanetary disks, right, you can also see some ratios that deviate a bit, but the ratios that we're deriving really look like some of the icy moon ratios that we've seen in the solar system. So it's a little bit speculative at this point, but it's certainly suggested in that direction. Yeah. Yeah, that's a great question. I would really love for there to be. So, I think what we need to look at. So, yeah, so what avenues could potentially exist? I mean, we don't have any direct evidence now, other than the fact that gas exists at these late stages, and that the accretion rates that are plausible that Kantan has included in his models do significantly impact the composition of the atmospheres. So there's that, right? That's what we have at the moment. How could we be more definitive? Well, I was discussing this with Nick earlier today. It would be really great to be able to see. I mean, it's kind of interesting to, like, now that we have some systems where we're seeing both a planet and a disk, including Beta Pic, which has a gas disk and a planet in it. It's really interesting to think, can we observationally put limits on accretion rates for planets that are embedded in these disks as we start to see more of these populations coinciding? And I was chatting with Nick today about, well, what would that even look like? Because if you have a hydrogen poor gas environment, can you look for H alpha? I don't actually know if you would see an H alpha accretion signature or not. So what would an accretion signature even look like for this carbon and oxygen rich gas? It's an interesting question that we don't really have an answer to yet. So I would like to see more modeling in that direction. That would be really exciting.
Related question.
Yeah.
In your little bit very high, right?
Yes, very high SNR.
So
Yeah.
do you see any perturbations?
Yeah, I mean, the big one is 49 SETI. That's the one that I showed that has this kind of spiral or warp in it. But then, yeah, so we've looked with Eddie and with some of the other tools that were developed for protoplanetary disks for, I don't know, it was partly by design, but now we're sort of wishing we had made different choices. You can see a lot of our systems are pretty close to edge on. So they're pretty high inclination, which is not optimal for doing that kind of work. Let me just find the gas slide here. So it's really not optimal for doing that kind of work. We have the best one. So I will say that in our first round of 10 ARKS papers, 3 of them are about HD 121617. So there's some evidence in HD 121617 of kind of hydrodynamic vortex-like gas deviations from Keplerian rotation on the edges of this system, kind of similar to where we saw the ARC in the asymmetries paper. So, so this one's very interesting, but you can see this one is pretty close to edge on. This one is pretty close to edge on. This one's so high inclination. We're not seeing anything at this point, but I think it's something that really should be done with the more close to face on gas bearing debris disks, but we don't have the high resolution in those cases. So we have a little bit of it. It wasn't really designed for that science case, although we've done the best we can with the data in hand at the moment.
Here, the top of the hour, but thank you, Meredith.